Section 7.6, Factoring ax squared plus bx plus c. So far, the only factoring of quadratic trinomials that we've looked at have had a lead coefficient of 1. In this example, we see a trinomial with an x squared and an x that has a lead coefficient of 3. This makes it a little bit more complicated, but we still have only a limited number of options to consider when trying to factor that trinomial. I want to try to use algebra tiles to help demonstrate the process for doing that. What I have depicted here is an algebra tile representation of 3x squared plus 5x plus 2. Now, in order to factor this using the algebra tiles, I'm going to try to fit all of these tiles into this space down here in our table. And I want to make sure that I form a rectangle when I do so. To start, I'll move my x squareds into place. Now, I have a couple of different ways I could set this up. If I go like this, I'm not actually going to be able to complete a rectangle because of this open space here. The only way to fill this open space would be with another x squared, but I don't have one. I've run out of options. So, I need to put this like that right there. Now I have my x squareds collectively forming their own individual rectangle. That's going to be an important piece to have going forward. Now I'll start to move my x's, and I want to make sure that my x's also form one or more rectangles within the shape. If I start to put them down here, if I just line them up again right next to each other, it doesn't leave me any place to put my two 1s because I can't just line them up right here. It doesn't work that way. And so I think that I have to come up with some other way to arrange these x's. Well, part of the problem is that they're all vertical. So let's change that real quick. Let's flip 3 of them on their side. There, that's better. Now, why did I bother doing that? Well, the reason I did is because now I can slide these underneath, and they actually fit a lot nicer underneath these 3 x squareds. And now you can see what's left. We just have this little space here, which seems like it would be perfectly situated for 2 little 1s. Now that I have a rectangle that's complete inside with algebra tiles, I can figure out what would go in this missing area. To figure out what would go first in each spot, I have to think about what times itself would equal x squared. Well, my only option is x times x. And so that's what I fill in to start. As I go across the right, I'll see that I need 2 more x's up there to generate these 2 x squareds. And now it's pretty easy to see what would complete each row or column. I need to have some 1s in there. A quick double check will show that these 2 binomials would multiply together to get 3x squared plus 5x plus 2. The one on top translates to 3x plus 2, and the one on the side is x plus 1. Which means that a factored form, or the factored form, of 3x squared plus 5x plus 2 would be 3x plus 2 times x plus 1. You can distribute, FOIL, multiply, Punnett square method, whatever you want, to show that this product ends up being exactly the same as that. So that's how we would use algebra tiles to see this. There are ways to do it without the algebra tiles, and that's what we're going to look at today. One thing to consider anytime we have a trinomial is to see if we can factor out the greatest common factor first. If every term has a greatest common factor greater than 1, we would want to factor that out of the polynomial completely and then proceed, as that will make the problem a lot easier to do. You notice that all 3 of these terms, 5x squared, 15x, and 10, are all divisible by 5. That will be our starting point. I'm going to take the 5 out by using a reverse distributive property. So that polynomial, that trinomial, will equal 5 times something. Well, 5 times something was 5x squared. That something has to be x squared. 5 times something is 15x. That must have been a positive 3x. 5 times something is 10. That's a positive 2. And now I have that my original trinomial is equal to 5 times a trinomial that I'm used to factoring. My lead coefficient is once again 1, so now I just try to consider what two numbers multiply to positive 2 and add up to 3. And of course, there's only one option for that. My original trinomial in its factored form would be equal to 5 times x plus 2 times x plus 1. Because my last term, my constant term, has a positive value, I know that these are both going to be the same. They're going to be the same as the coefficient of the middle term, the 3x, which is positive, and so that just kind of double checks it right there. Quick FOIL will show that that's the correct answer. First thing you need to do anytime you see a trinomial is look for a GCF. It can save you a lot of time and a lot of trouble. All right, let's take a look at two examples right here where we can't take out a GCF. We have 4x squared plus 13x plus 3 and 3x squared minus 7x plus 2. What we'd need to do is we'd look for a GCF, but there's nothing that all three terms have in common in each of these problems. So the first thing we'll consider is whether the product of the lead coefficient and the constant term is positive or negative. And in this case, it's positive. Positive 4 times positive 3 is positive 12. Positive 3 times positive 2 is positive 6. And so what we have to do is we have to think about the numbers that are going to multiply to 4 and the numbers that are going to multiply to 3. And so in terms of multiplying to 4, there are really only two options here. It's 1 and 4, or it's 2 and 2. And for 3, it's only going to be 1 times 3. Now because this is positive and this is positive, I have all positives here, I know that I'm only dealing with positive numbers. I don't need to worry about, well, what if it's negative 1 times negative 3? All right, so that's going to make it a little bit easier to consider. Using this here, I'm going to just do a little bit of trial and error. I'm going to set up possible answers and see if they work. I will take the 1 and 4 and set those up as coefficients of my x's. So I'm going to have 1x and I'm going to have 4x. And now I'm going to, as a constant term, get those from 1 and 3. And so I'm going to put plus 1 plus 3. That's one option. Now at the same time, I could have a different option, which is x plus 3, 4x plus 1. Because those are two different problems. Still, I know that I'm going to end up getting my 4x squareds and my 3, but I have to make sure that I have it set up in the correct order. Finally, I have one last option. Rather than 1 and 4, I could have used 2 and 2 for the x's, so I could be looking at 2x plus 1, 2x plus 3. Once again, you'll notice that in all three of these cases, when I FOIL, my firsts will multiply to 4x squared. My lasts will multiply to 3. The key is only one of these is going to be able to give me 13x in the middle. All I have to do is check that and I'll know which one is my correct answer. When I do the outside and inside for the first one, I get x times 3 is 3x, 1 times 4x is 4x. Adding those together, and my middle term here is going to be 7x. That's no good. I don't want to use that one, so I'm not going to count that as my answer. Check out the second one. Outside term is x. Inside term is 3 times 4x, which is 12x. Add those together, and I get 13x. That's the answer that I want. That's what I'm looking for. As soon as I do that, I can disregard my last option, because that was the only chance that I had to make it work. So this means that the correct factored form of my trinomial is x plus 3 times 4x plus 1. It takes some trial and error, some kind of intelligent or educated guessing, but you can get there. We can follow the same process to factor 3x squared minus 7x plus 2. Once again, I want to think about the factors of 3 and the factors of 2. This is actually even a little bit nicer than the last time, because the only way to multiply and get 3 is going to be 1 and 3, and the only way to multiply and get 2 is 1 and 2. So we're going to set up our candidates here, and we're going to say that we're going to have either 1x times 3x, and then on the back end we have to have a 1 or a 2, and now we can either have it there or we can have it like this, so that we have the different combinations available. Now we want to figure out what symbol would go in between there. Well, because this is positive, I know the symbols are going to be the same. They're both going to be the same as the middle, which is negative. So this right here is going to be a negative on all cases. Now we just check each one by multiplying. We know that with the first and with the last, I'm going to end up with 3x squared and positive 2, because I set it up that way. So what I check for is the middle. In the first example, I have the outside is negative 2x, and then here I have negative 3x. That's going to be a combination or a sum of negative 5x. And on the bottom, when I multiply, I've got negative x and negative 6x, which combines to be negative 7x. That's just the outside and inside combined. That's the one that I want. That matches the negative 7x in the middle of my original. So I do not want to use the first factored form, but I do want to use the second. You can multiply that out just to double check, but that will be the factored form of 3x squared minus 7x plus 2. Okay, let's continue and try to figure this out when the product of AC is negative. In this case, AC would be 2 times negative 7, which would be negative 14. And so that's a negative value. So what we're going to end up with is a factored form which contains, sorry about that, I don't necessarily know that that's going to be an x, but I do know that I'm going to have something x plus a number and something x minus a number. And so that's what I'll have to figure out. That's going to give me a couple of more options to consider here. Now, once again, we want to consider the two different coefficients, the lead coefficient and the constant term, figure out how we can multiply and get those numbers. How do we multiply to 2? That's just 1 and 2. How do we multiply to 7? Well, fortunately, that's also prime, so that's only 1 and 7. So now we have to consider our options. So the coefficients of x are going to be 1 and 2. We're going to be looking at x, and we're going to be looking at 2x. We're going to be looking at x and 2x, because we have different options here. And so perhaps the 1 goes with the x. Oops, sorry about that. And the 7 would go with the 2. Or perhaps the 7 would go with the x and the 1 would go with 2. But those aren't actually our only two options, because here I could switch things around. I could have plus or minus with each of these, or I could change the location of the pluses and minuses. So I also have to consider x minus 1, 2x plus 7, and x minus 7, 2x plus 1. And so those are actually the 4 options that I have to consider here. Those are the 4 different ways that I can multiply and end up with 2x squared when I do my firsts, and negative 7 when I do my lasts. Those are the only different ways there. So once again, I just check for the middle term by combining the outside and inside products. This is negative 7x plus 2x, and negative 7x plus 2x is negative 5x. Wow, we're done. We don't even need to go any further. We've got it done already. Our final answer is going to be x plus 1 equals 2x minus 7. That's the factored form that we want for, that we were looking for. I'm going to show you what the middle term would be for each of the other three anyways, but you can see that they're not -5, which is what we wanted. So here you see the middle terms. When we multiply out each of these, we get a positive 5x, a 13x, and a negative 13x, none of which match up with the -5 that we want to have. So in this case, we happen to guess luckily and get it right the first time. Sometimes that'll work out, sometimes it won't. Okay, what happens when a is negative? Looking at this here, we have a coefficient of the x squared term, which is -4. There's nothing particularly different about this, but for some reason, having a negative value makes it a lot harder to deal with. So my suggestion for this is to change the sign of everything and just factor out a negative in front of the entire polynomial. Rewrite this as negative times the quantity 4x squared plus 8x minus 5. You can see that if we were to distribute that -1 back into the trinomial, we'd end up back with our original quadratic trinomial. Now we have a situation just like the last problem. I have to figure out what combination of terms are going to multiply to give me 4x squared and -5, and then try them out to make sure I end up with 8x. The ways to multiply and get 4 are 1 and 4, or 2 and 2. The way to multiply and get 5 is just 1 and 5. And so there are different ways that we can try this here. Try the different combinations like you did on the last page, and you just hope that you get lucky. So we'll try to do this here, and we'll say that maybe, we'll just take a guess, maybe I'm going to start with 4x plus 1, and then 1x minus 5. Something like that there. Using the 4 and 1 as this possibility, and the 1 and 5 as this possibility. And we know that the first will multiply to 4x squared, the last will multiply to -5. So once again, we just check the middle term, make sure it's going to work out. And that's going to be -20x plus x is a -19x. That's way off. That's a kind of a bad sign. Definitely don't want to do it this way. We wanted to get positive 8 because of the way that we had moved it around, and that's not it. So we'll just try something else. Again, a lot of it is kind of guessing and checking here. So I'm going to go with 2x, let's say, plus 5, and we'll do 2x minus 1. Again, just kind of guessing and seeing if we can make it work. Once again, our firsts are the 4x squared, the last are -5, so we just do our middle term. That's -2x plus 10x actually gives us the 8x that we want, because we have to look at this version here. This is what we were looking to get, and so that's the part of the expression that's in the parentheses. So for my final answer, I just need to make sure that I include the negative. That's going to be -2x plus 5, 2x minus 1. And that's going to be my final answer. So once again, just some guessing and checking. There's a few different combinations we'd have to look at. Hopefully you get lucky and get it sooner rather than later. All right, now it's your turn. Here are 4 problems that need to be factored. None of them are prime, and I want you to go through each of these problems after you pause the video, and then come back to check your work. Good luck. Now it's time to reveal the answers. And there you have it. Those are the 4 solutions that you want to look for. Pause the video so that you can double check your work. Quick notes, the first one just involved a greatest common factor of 8. The last one involved removing a common factor of a negative and then working with a kind of a normal problem from there. And then the other 2 problems are relatively straightforward, just took a little trial and error. All right, hope that went well. All right, let's see if we can use this factoring method in order to solve a word problem. The length of a rectangular game reserve is 1 mile longer than twice the width. The area of the reserve is 55 square miles. What is the width of the reserve? Well, to start off, I think we need a picture. Here we have the rectangular reserve, and we can label its width and its length. Now we know that the length is 1 mile longer than twice the width. That means we can replace the L for length with 1 plus 2W. We also know that the area of the entire reserve is 55 square miles. So what we're looking to do here is combine the information we know with the information that we want to know to solve for W, which is the width of the reserve. Now, we know that the formula for the area of a rectangle is length times width. We know the area is 55, and we know the length is 1 plus 2W, and the width is W. We're going to distribute the W here to both of my terms within the parentheses. And remember that anytime I'm trying to solve an equation like this, I need to make sure that I have 0 on one side of the equation. So I'm going to subtract 55 from the other side of the equation, from both sides. Then I'm just going to rewrite my answer in standard form. So after rewriting our equation, we have 0 equals 2W squared plus W minus 55. Now we just go ahead and we try to figure out the proper way to factor this. A little bit of trial and error will help us arrive at our final answer in its factored form. So after considering all of our options, to multiply to get 2, we would have to use 2 and 1. And to get 55, we'd have to either use 1 and 55 or 5 and 11, and make sure that one of those is negative because we have a negative 55. Move things around, trial and error, we end up getting that 0 equals 2W plus 11, and then W minus 5 as our two factors. Now we can use the zero product property, set each of those pieces equal to 0, and we get our answers. In the first case, W would equal negative 11 halves, or negative 5.5. In the second case, W would equal 5. Now, we have to consider in the context of the problem which one of these works. We certainly can't have a width of an actual rectangle that is negative, so I'm going to disregard negative 11 halves as my answer, and I will use W equals 5. Go back to check in our equation, or in our diagram, excuse me, and we find that that width of 5 miles would give us a length of, well, 1 plus 2W would be 11 miles. And sure enough, that gives us a rectangle with the area of 55 square miles, which is exactly what we need. So by looking back at the question, we were able to disregard one of our answers and select the one that is the actual solution.